This is part 3 of my Mini-Lathe project. So I've got the Mini-Lathe set up, so it's all clean, degritted, adjusted. Seems to do a fairly good cut on aluminium at least, so I think that's good to go. The rest of this project's around setting up a stepper motor to run the lead screw here, so that moves the carriage up and down the lathe when I'm cutting things on the lathe. So this one I'll look at the electronics for the actual speed controller. I covered some of it in part 1, but this will sort of finish it off, and then I'll also look at mounting the motor on the lathe and maybe do some test runs, make sure the motor's got enough torque, those sort of things. So we'll see how we get on. For the stepper motor controller, I'm going to do the same as I normally do. I use one of these breadboard style PCBs, and I put the RPI Pico, attach it to it, look about there. This time I'm not going to socket this one. In the past I've been socketing these and I don't think I really need to, so I think I'll just solder these directly. See, these have got castellations on here, so I should be able to just solder those directly on. And I think I'll only need to solder the pins that I'm actually going to use, so I won't solder all of them. I'll just solder the pins I need to. I did check that this board's working, the Pico's working, so we should be good to go. So let me get that soldered together and see what it looks like. Masking tape down the board so it doesn't move around when I start on this. I've listed out the pins I need to solder on. Again, I'm not going to solder all of them, so let's start on this. Wasn't sure how good my soldering went. I hadn't soldered these sort of castellations before, so I put it under my microscope to check on how the solder flowed. So these are all the joints. Looks like it flowed well, everything joins up, but I can't see any obvious dry joints, so I think I'm going to go with this. This seems fine. For testing out the PCB in the motor, I made some changes. So on the PCB I also added this buck converter. It's a variable one, so it goes from up to 40 volts down to, and I set it to 5 volts. So that's going to power the RPI Pico and still have it'll be 24 volts available for the actual motor driver. As well, down here I made some mounts, just 3D printed those. I'll include the file I use for that. It's nothing sophisticated, but just made some mounts, and I used existing screw holes in this driver to mount those. So now those will go together here, and I can put some screws down there to keep all this together. The other thing I did is I soldered some more GPIO pins out on this side, because I think I'm actually going to be running the wires from this side down to the motor controller. So things like enable the pulse width speed and the direction wires will go down here. So most of the stuff is going to be on this side. I use these two wires here for the I2C to the OLED, and then I'll use this side, a couple of, probably 3 of them, GPIOs to manage the rotary encoder. So I'm going to wire that up and then show you the result after that. Here's the wired up PCB, and I've got it connected to the motor controller there. So this buck converter gets power. So originally the 24 volts comes in on this connector and goes to the driver, and then is also diverted to this buck converter, which drops it down to 5 volts, which powers the Pi Pico. Otherwise I've wired up all the enable, direction and pulse pins to go to the motor controller here, and I've wired up the rotary encoder, which gets power from here, and these pins here gets the values off the rotary encoder. And I also added the switch, so there's a switch here where you push the rotary encoder, it'll flip a switch, and I use that to reset the value on the rotary encoder, so it brings everything back down to 0, so it basically stops the motor, which will be useful when I'm using it on the lathe. I can just press it to, if I want to stop the motor going altogether for the lead screw. So let's try this out. So here's the motor connected. I'll show you how I set up this connection to the lead screw next in a little while. So I've turned the power on. By default it has a value of 0, so if I start turning this you can see the motor changing, and if I press the button resets it. Okay, both directions. It's a little wobbly here, but I don't think that'll matter for the lead screw. I'll see how close I have to be, and I can probably adjust it here to get it right. But that's looking good, so I think I can try that out on the lathe, or at least mock it up on the lathe to see whether it actually turns the lead screw the way I'm expecting. Let's have a look at the changes I made to my Micropython program, and there's more details on this in the previous video, I think video 1. But I changed the pins that are being used after wiring it up. I used some different pins on the Pi Pico. I added these 2 pins, so one is this is break pin, so it allows you to break out of the main loop. For some reason I don't seem to be able to break out of the main loop using the keyboard, so when I'm iterating the programming it locks up and I can't update the code. So is break pin allows me to break out of the main loop just by having a little switch on the board. And this is reset pin is something I added. So on the rotary encoder there's also a switch where if you press the rotary encoder I'll send a close a switch, and that's what this pin here is listening to, and that's used to reset the value on the rotary encoder. Otherwise code's almost exactly the same as I showed in the earlier video. You see the conditions in here to either break out of the main loop when that break pin is, or that break switch is pressed, and where I reset the rotary encoder's value if the rotary encoder switch is pressed. Otherwise it's the same going through here. Just a reminder from the part 1 video, this was my original design, so I'm using a quick change 14mm hex shank connected to a 6.3mm to 5mm coupler connected to the actual motor. So let's have a look at putting this actually together. So I needed to machine the hex shank, so first I found the center in the back, then punched a hole right in the center, and then drilled a little hole right in the center so I could use that for the tailstock center on my lathe. So I could mount the whole thing in the lathe, and I'm just taking the hex fitting down to try and make it as round as possible. I think I should be able to get it down to 6.3mm. It will fit into the coupler I got pretty nicely. So I was playing around with speed, and you hear it not sounding very smooth at the moment, mainly because I'm turning down the hex side, so it's going to hit and then be free of the metal as it rotates. So it's going to make a pretty horrible chunky noise, but as I work through it, it smoothed out, especially once I got it down to being round. I could only go so far before I get too close to the chuck. I'm worried about hitting it with the tool holder, so probably only went about 10 millimeters. Once I had enough turned down, then I just wanted to cut off the end that I wasn't going to be using on the hex shank. And I think I just need to file that down a bit. So first I wanted to put a flat on one side of the round to be able to get the coupler to connect better. I may not have needed to do that, but it'll be useful. So I just used the file to flatten one side. It really didn't take much. And once that was flat enough, I thought would be a grub screw contact with it. It should be enough. I notice there's a bit burred up at the end of this as well from where I hacksawed it off, so I just filed that down too while I had it in the vise. All good. So I connected these together and put it on the motor and did a trial fit on the lathe. So let's have a look at that. This is my first test on the lathe, so we'll find out whether that Nema 17 motor's got enough torque to turn the lead screw. You can see how I set it up here. Basically made kludged together a L-shaped bracket to hold the motor and the coupler and the 40mm hex nut onto the back of the lathe. Connected it all up. I got my power supply here. It's actually delivering 24 volts at maximum of 2 amps. So let's fire it up. So you see when it's 0 speed, basically it's not drawing any current at all. We see it's having problems turning the lead screw, so looks like I don't have enough torque. Again, that's just the lower speed, set for 1 at the moment, so let's push up the speed, see if we get any more torque. It just seems to be getting stuck partway around turning the lead screw, so there must be a bit more torque needed in certain positions. I can start it going and then it stops again. So this is telling me I need a bigger motor or geared up, some gears in there. So it looks like I'll have to stop until I get that done. I just thought one more thing I want to try is the peak current delivered. So currently I had the driver set for 1.7 amps peak current, so I pushed it up to 4 amp peak current and fired up the power supply. Also made sure I could deliver quite a bit of current through that power supply, so I put it on actually 3.5 amps. Turned it on. And don't seem to have much of a torque problem. And I locked down the bed here to the lead screw and seem to be able to move the lead screw with a bit of graunching, so it's probably still on the limit of the torque. See, it really got stuck there. So even with increased current, I definitely needed more torque. So I went with a geared stepper motor, still a Nema 17 version, but it had a larger axle of 8mm, so I had to get a different coupler for that. The stepper motor hasn't arrived yet, so in the meantime I thought I'd add an OLED onto the board. So you can here see the OLED's turned on, displays by default revs per minute. But I also added a switch where I can switch between modes, so now it's showing revs per second. If I push it again, it shows
the inches that the carriage would move per minute as well. You can see I can change the speed from the dial, same old way. And the switch will allow me to flip through the 3 modes. So again, you'll see the different modes here. Let's have a look at what that looks like in code. So back into the main.py code. So I added 3 main files, this writer pi, SSD 1306pi, which are libraries, and then this free sans num35, which is a 35-point font mapped to bitmaps in a file, and you'll see where that's been used. And if you look back in my Baysian Calculator set of videos too, I get into more detail about how the OLEDs run to allow a larger font size to be used to display digits. Let's have a look at the code here. So I'm importing the FreeSAN S35. I'm importing from machine. I'm also importing I2C now because I'm using that as my interface to the OLED. And then I'm importing these 2 libraries. The SSD 1306 is the basic library for interfacing through I2C to the OLED display. Then this writer library, it came from Peter Hitch, and that allows me to write the bitmapped fonts which are larger fonts onto the OLED. I added some constants in here, so for calculating the speed, the steps per revolution that the stepper motor controller is set up to. So you do that with dip switch. My one's at the moment set up for 1600. When I've got a stepper motor with gearing, it should be 14:1 gearing on the stepper motor, so that's been used in the calculation in revs per minute. And for calculating the inches that the carriage moves per revolution, I use the information about the lead screws threads per inches, which looks like it's 17 on mine. I added a variable. Goes through the values of 1, 2, or 3, depending on whether we're showing revolutions per minute, revolutions per second, or inches per minute. I set up the I2C interface, so that's using pins 17 and 16 on my board, and it's on bus number 0. And then I set up the OLED object using this SSD 1306 interface, and that's where you specify what the OLED size is, what I2C bus it's using, and what address is set on the OLED. I set up this WRI or writer object, and that's going to manage the writing of the larger bitmap numbers to the OLED. Just do some of the housekeeping we saw in the earlier videos, but I also added this this pin, which is going to watch the switch where I change the mode of the display between revs per second, revs per minute, and inches per minute. So this is just a simple switch, and later on I'm going to be debouncing that, or doing some simple debouncing of that. When we get into the main loop, so now we've added this condition where it's either the value of the speed that we want is changed, or else the display mode pin. So that pin I just set up for switching between display modes, whenever that changes from a value I'm storing, and again this loop goes through every 50 milliseconds, so it only checks every 50 milliseconds, so that effectively debounces the switch. If the display mode pin has changed from the earlier value, so this is specific to that condition, and the display mode pin is equal to 0, so I only want to do it on the press of the button, not the release of the button, it increments the display mode, or if it gets to a value of 4, then it takes it back to 1, so it just cycles through 1, 2, and 3 like we saw. And we also set the old display mode pin to what the new value is, so we can check against that for any changes in future cycles through this. Most of this is the same as I showed you earlier. There's the calculations for depending on the display mode, so different calculations here based on the gearing and the pulse ratio on the stepper. whether we're doing things in seconds or minutes, all this sort of thing. It also changes some parameters about how many significant digits I show. So for the geared motor, for some of these things it shows, it's better to show 2 decimal places. For others, just 1 decimal place should be plenty. And also sets the prompt it's going to display. And then for displaying the information, it's doing it in sort of 2 cuts. So one with the normal SSD text and font. So this is the small font, so it displays the prompt at the top of the screen. Centering it using this format command here. And then it's also using the writer control here to display the numbers, and depending on whether it's 1 or 2 significant digits, then it displays the numbers with 1 or 2 significant digits. And that's the loop. Again, sleeps 50 milliseconds in between. So that's all set. So once I get the geared motor, we'll connect that up and see how that runs in the lathe. The new geared stepper motor arrived, so I hooked it up. It wasn't very hard to do. Because it's Nema 17 still, it mostly fitted in the same bracket. I just had to add some screw holes, move the screws in a little bit, but otherwise it fitted quite nicely in the bracket, so pretty easy to set up. So you can see here it's using the same controller, but because it's a 14:1 gear ratio, it moves a lot slower than before, so it should have a lot more torque too. So this is looking good. So while I had on my workbench, I thought I'd also test out my speed display. So I set it up to run at 1 revolution per minute, set my stopwatch, looked at where the motor is located, so you can see that line on top of the gearing shows you the current location at 0 seconds, and now after a minute you can see the lines back up to the top, so it really is moving 1 rev per minute. Looks good. So I attached the new geared stepper motor to the lathe in the same way as before. Nice thing is it uses the same bracket, so it wasn't too hard to do. Started it up. Looks like it starts. Doesn't seem to have any torque problems, but this is the real test, is when I engage the lead. Again, still turning nicely. So it looks like the torque problems are solved with this geared motor, which is kind of what I'd expect, is just on the limit. When I was using the ungeared motor, so at a 14:1 gear ratio, it should have 14 times more torque. So I'm going to say that's a success. So while I have it on my lathe, I also wanted to test another display option, so the inches per second, see if my calculation's correct. So at the moment I've got the tool set up to be 4 inches away from the work. So I didn't photograph the ruler very well there, but it said 4 inches. I'm going to rev up the speed to, now it's 1.51 inches per second on my display. Now I've got my stopwatch going again. So I'll let this go for a minute and see how much the tool moves. Speed up this bit and stopped it after a minute. And let's measure it. So it should have moved like 1.5 inches based on my calculations on the speed controller. And my immediate reading on the ruler is 2.5 inches, so it's gone from 4 inches down to 2.5 inches, which is 1.5 inches, so that's a success as well. Let's try some turning. So I've got a piece of aluminium in here. I've started the lathe running, starting to get the cut to the depth I want. And let's turn on the motor. The carriage should start moving now. we go. And we can see the cutting going on here. I'll probably do a little deeper than I'm doing here, but this allows me to have a look at the finish. That seems to be going okay. Not sure whether I want to be able to do more speed. This is the max speed moving down the bed at the moment, so I may want to change the speed on it. But that finish looks good. So that's it for this part of the video. Next video is probably going to be more on finishing things up, so doing a more permanent mount to the lathe for the motor, and then putting all the electronics in a control box, and I may even do some more changes to the electronics. I may put in a function where you can just have it move up to a certain point and then stop, and that'll be useful for doing repeated cuts.